Welcome to the third lecture of Laplace series. So today's topic is the convolution of the functions. Convolution of functions. First of all, let us understand the concept that how to get the convolution of two functions. Let ft and gt be any two functions then convolution of ft and gt is denoted as ft star gt. It is the notation. Now mathematically ft star gt is defined as integral 0 to t f of t minus u gu du. This way we used to define the convolution of two functions. Now we know that by property of definite integral 0 to a fx dx is same as integral 0 to a f of a minus x dx. So therefore I can write this as integral 0 to t f of, what should I write here? I can replace this as t minus of u g of t minus u du. So therefore this t will get cancelled with this. This is integral 0 to t f of u g of t minus u du. Okay, so I can say that this is the way of defining the convolution of two functions. Now let us understand this concept in the depth, that how actually we are defining the convolution of two functions. Now to understand this concept in the great depth, I am removing this part. I am removing this part. Okay. What I had defined that ft star gt as the integral 0 to t f of t minus u into g of u du, which is same as 0 of t f of u into g of t minus u du. In either of the way you can write it. Suppose I am having the function, I have to calculate the convolution of t star e to the power t. Now let us understand this concept. What it will be? It will be integral 0 to t minus u into e to the power u du. Yes, of course we can write it this way. By definition, by retaining f of t as t and g of t as e to the power t, I can write this way. So now integrating it by parts, so what I will get if I use the by parts condition here, since I have to integrate it with respect to say u, so the integral will be somewhat like that, t minus u e to the power u minus plus, and it will be simply e to the power u, simply integral 0 to t. So which is same as when u is equal to t, that is what we call, it will be 0 minus what I will get t, and then plus from here I will get e to the power t minus 1. So simply what I will get from this fact, look at here, actually when u is equal to t, that is t minus u is 0, and it is something like that, and when u is equal to 0, it is simply minus t. So it is like that. So we have e to the power t minus 1 plus t. So this will be the convolution. Another example I want to take again. Suppose I have to find convolution of t star sin t. What it will be? It will be integral 0 to t minus u into sin u du. Now integrating it by parts, so then what I will get? T minus u, okay, and simply what I will get further, it will be minus cos of u minus, okay, what will be the derivative of this? Derivative of this with respect to u will be minus 1, and again this integral of this quantity, then it will be minus sin u integral 0 to t. So finally what I will get? U minus t into cos of u integral 0 to t minus, this will again minus, that is sin u 0 to t. Now look at here, it will be 0 minus okay, when u is 0 then it will be plus, I think at t equal to 0, that is t minus t into cos of t minus, what I will get here, u is 0, then I think simply plus t, like that, and minus what I will get from here, sine of t minus 0. So finally what I will get? T minus sin t will be the convolution of this. So now this is all about the convolution of the functions. Now the next question arises, what is the application of these convolutions in the Laplace transformation? So for that we have an important theorem that is known as the Convolution Theorem. Now let us understand the application of Convolution Theorem. What is Convolution Theorem? Understand the concept. Convolution Theorem. Convolution Theorem. What this theorem says, that if you know the Laplace of ft, which is nothing but f of s, and you also know the Laplace of g of t, which is g of s, then this theorem says that then L of ft star gt is simply fs into g of s, which is same as L of ft into L of gt. It means that the Laplace of convolution is the product of their Laplace transformation. Okay. Now let us understand the application of this. Right now we have found the Laplace of this. According to this result, it should be like that, Laplace of t into and then Laplace of sin t. It should be like that. Now what is this? It is 1 by s square. What about this? 1 upon 1 plus s square. So that is, this is the right hand side. Now but Laplace of t star sin t. Now we have already calculated the convolution of t star sin t, which was t minus sin t. It was like that, which is same as Laplace of 1 by t is 1 by s square minus 1 upon 1 plus s square. Okay, if I simplify it, what I will get? So this motivates us that this theorem is applicable in such type of condition, that is Laplace of convolution is the product of their Laplace transformation. Okay, now the proof of the theorem, that is also really significant for exam point of view. Okay, so now let us understand the proof of the theorem. So now I'm erasing this because I'm having the little bit space, so I have to optimize my space as well. So now let us understand the proof of convolution theorem. What I want to prove, first of all, write to prove Laplace of ft star gt as Laplace of ft into Laplace of gt. This thing I want to prove. Now step 1. By definition, Laplace of ft star gt will be simply integral 0 to infinity e to the power minus st of simply ft star gt, and in the I have gt, but ft star gt is same as integral 0 to t f of t minus u into g of u t. Let it be 1 and let it be 2. So using 2 in 1, then what I will get? So therefore Laplace of ft star gt as integral 0 to infinity e to the power minus st. If I substitute the value, then what I will get? Integral 0 to t f of t minus u g of u dt du, somewhat like that. Now if I get the value of this double integral, then we are done. So now again I'm reviewing some of the lines of this proof because the proof is somewhat lengthy. I cannot say it is lengthy, but I am writing somewhat big size font, so that is why it is appearing like as a big proof. So I'm removing this part. Now let us understand that. So now we have obtained up to this part. I can write this as L of ft star gt as integral 0 to infinity, integral 0 to t, e to the power minus st, f of t minus u, g of u, dt, du. I can write this way. Okay, if it is the case, now what I will do, it is a problem of double integral, changing the order of integration. Now first of all, first step, current region. Let us draw in this region. Okay, if I am drawing this region, if I take this as my t equal to 0 axis and this is u equal to 0 axis, and then this is the line u equal to t. Okay, as t is varying from, these are the limit of t and these are the limit of u. So this is the line u equal to t. So now as t is varying from where to where? 0 to infinity. So in fact in this particular direction, in this particular direction. So t is varying. And u is varying from where to where? It is like that. So earlier we had taken this horizontal strip in this region. Now if I take this, in fact this vertical strip we had taken, I sorry to say as a horizontal strip. Now in order to change the order of this integration, I am taking the horizontal strip corresponding to this region. So the limits corresponding to horizontal strip are, your t will vary from where to where? U to infinity, and u will vary from where to where? 0 to infinity. So I will use these limits here to establish the proof of this convolution theorem. So therefore let it be say 3. Therefore 3 can be written as f3 can be written as, simply I can replace these limits as the t varies from where to where, u to infinity, and u varies from where to where, 0 to infinity. Okay, so please you note up to this part, and then I will start from this part. So these are my limits. These are my limits that I want to use. Okay, so now I am removing this particular part, so that you will understand this concept also. Now let us understand this. Now this double integral will now become, now as t is varying from where to where, t is varying from, now u is also varying from 0 to infinity, and t is varying from where to where, u to infinity. I can write this as e to the power minus st f of t minus u dt, and then g of u dt. Okay. Now what I will do here in this inner integral, let t minus u is equal to v, so therefore dt is equal to dv, so therefore we will vary from where to where, 0 to infinity. So therefore this integral will become u 0 to infinity, v again 0 to infinity, e to the power minus s u plus v. Now what is t minus of this? That is f of v dv gu du. It is like that. So now we are almost through the proof of this theorem. So now let us understand one more important thing from here. So I can write this as further, u varies from 0 to infinity, v varies from 0 to infinity, e to the power minus su, e to the power minus sv, fv, gu, du, dv, up to this part. Okay, now I think we are almost through to the proof of this convolution theorem. So now I am removing this particular part. So now what we have achieved up to now, so I can write, so finally, that is from this point onward, from star onwards, that is Laplace of ft star gt as is equal to, I can write u as 0 to infinity, e to the power minus su, I think it is g of u du, and then integral v from 0 to infinity, e to the power minus sv, fv dv. Now I can remove this part also. So it is nothing but, it is g of s and it is f of s, which is same as Laplace of ft into Laplace of gt. So this proves the convolution theorem. Now some important deduction that I want to get from the convolution theorem. Let us understand that particular part also. Okay, so I am removing this particular part also. Some important deduction from convolution theorem. Some important deduction from CT means convolution theorem. Please understand that CT means convolution theorem in order to minimize the time. Okay, if I take my ft as, say simply ft, and gt as 1, then what is the convolution of 1 star ft? First of all, you check this convolution. What will be this convolution? According to the definition, this convolution will be simply equal to, if we calculate this convolution according to us, I think it should be like that, integral 0 to t. If I take this as my so one function, that is 1 into fu du, like that. So by convolution theorem, by CT theorem, that is what we call convolution theorem, Laplace of 1 star ft should be equal to Laplace of 1 into Laplace of f of t. So this will imply Laplace of this. What is the convolution of 1 star ft, which is integral 0 to t f of u du. What is Laplace of 1? 1 by s. What is Laplace of ft? If I assume that, say fs, so that is fs by s. So it is an important result that we got from the convolution theorem. What this result is saying, that the Laplace of an integral is nothing but you first get the Laplace of this and divide this result by s. For example, suppose I have to find the Laplace of this. Suppose if somebody asks you, what is the Laplace of the integral 0 to t sine u du? Now we know that the Laplace of sine t is simply 1 upon plus s square. So it is simply, if I take this as my fs, it should be like that, fs by s, that is s into 1 plus s square. It is like that. So these are some important application of a convolution theorem. Now my next concept is of an Heaviside unit step function. That is also an equally important function in a Laplace transformation. So for timing, I am removing this one also. Heaviside unit step function. What I am defining? Let A be any real number. A be any constant. Then unit step function at t equal to a is denoted as u of t minus a, or sometimes you write u of ta or h of t minus a. Either of these notation can be used. Either of these notation can be used. Mathematically, we define u of t minus a as it is 0 when t is less than or equal to a, which is greater, you see, and it is 1 when t is bigger than a. This way of defining the Heaviside unit step function. Now graphically this function is somewhat like that. If I take this as point A, so through this the function is like that, and suppose this distance is unit distance, so it is like that. So it has this jump discontinuity at t equal to a. So that is why it is known as the step function. Now see that what is the length of this step? The length of this step is 1. That is what we call unit step function. That is because of this unit step we have the jump discontinuity. So therefore it is a Heaviside unit step function. Okay. So now we are moving towards that how to get the Laplace transformation of an unit step function. That is an also important application. So now for timing I am removing this also. Laplace of unit step function. What is the Laplace of unit step function? Laplace of unit step function. By definition, u of t minus a is simply, what was the case? 0. And it is 1 when t is bigger than a. So the L of u of t minus a should be like that, integral 0 to infinity e to the power minus st u of t minus a dt, which is same as integral 0 to, what should I write? A e to the power minus st u of t minus a dt. Then second part, from where to where? A to infinity e to the power minus st u of t minus a dt. Now in this domain, the unit step function takes the value 0, and here it takes the value 1. So finally, what we left with? We left with integral 0 to infinity e to the power minus, in fact not 0 to infinity, a to infinity. Now if I integrate it, then what I will get? E to the power minus st by minus s, from where to where? A to infinity. So which is nothing but, at infinity it is 0 minus e to the power minus sa minus, what should I get? Minus s. So it is nothing but e to the power minus sa by s. So this is the Laplace transformation of an Heaviside unit step function. Okay, so now we'll do in the fourth lecture. So I'm keeping the concept up to this point only. So now in the fourth lecture I will move from this point onward, so to do the application of unit step function in the Laplace transformation. So that's the end of the third lecture of units of Laplace transformation. So goodbye for time.